All right. We are oh, you stole my line, but you're right. We are still on chapter 14 here. We'll eventually get to 15 at some point before June, I suppose. So chapter 14, we're into kind of the second half here. And last time we talked about buffers, and obviously, as we've talked about, buffers are again solutions that can resist changes to pH when you add more acid or base to it. Really big changes in pH, as we talked about. And again, as we talked about, really the reason they're able to do that is what they're made of, a weak acid and its conjugate base, or the salt of its conjugate base, are a weak base, and the salt of its conjugate acid. We talked about calculating pHs of buffers, which are really common ions, and we can use, again, our Henderson-Hasselbalch equation. And again, the cautionary note of the Henderson-Hasselbalch equation is it is really only for a buffer situation, common ion situation. So again, you don't want to get into the habit of just kind of always using it in every situation. It is really specific for just buffers, where the pKa obviously is minus the log of the Ka value. We talked about when we add acid or base to a buffer, remember that we do need to do an ice table, and we should do this ice table in moles. And again, not molarity, as the molarity will change as we mix solutions together as they get diluted, but the moles will stay the same. And we should do this first ice table in terms of moles. Also different in sort of these ice tables as well is, and typically I would say in most cases, if you're doing sort of an ice table with moles, a lot of times you will know what the change is. So we kind of know what the change is. And in a lot of cases here, it should be really the acid or base that you're adding to the buffer. It should also be the smaller number of moles is always the one you want to, again, choose when you're going to do that. And so we'll actually use a number here. And what you should end up with after that first ice table is still the same buffer left over. It's really, like I said before, good practice to convert it back into molarity at that point using the total volume. Because in a lot of cases, as you continue on, especially what we're going to talk about next, which is titrations, you will need it in molarity. So everything will be sort of in the right unit. So that's just a really good way. Um, Although, as we did talk about, technically speaking, you can go into here with moles of each of those, and it will work out the same because the volumes will cancel anyways. But if you chose not to do, for example, the Henderson-Hasselbalch, and you're going to do an ice table instead, you really probably should use molarity there in that ice table, which is our alternative version. Remember that if the buffer is working correctly, we should not see a really big change in pHs. But when you do these type of calculations that involve adding acid or base to your buffer, you will see a change in pH. And again, that change should be relatively small. It shouldn't be a really big jump, but it's a good way to check yourself after you do a calculation. So for example, if you added an acid to a buffer, your pH after you add the acid should have gone down a little bit, right? So again, if you did the calculation and it went up, then clearly something went wrong with your calculation and stuff like that. So those are ways that you can kind of check out your calculation. Any question on buffers before we move on? All right, then it is the next big topic of the season here, which is everybody's favorite, titrations. Yes. Thank you. They're very nice. And the dreaded pink color, perhaps. Yes, I don't know. So when we do a titration, we usually have two types of solutions. We usually have a known solution, and what we know about that solution is the molarity. And a lot of times when we do a titration, we oftentimes will have like an unknown solution where maybe we don't know the molarity or something of that nature. So a lot of times we can use a titration to figure out, for example, and using stoichiometry to figure out the molarity of an unknown, say, acid or an unknown base. And in a titration, we typically use our burette, wonderfully drawn here as a arrow pointing down. And when we have a burette, we usually add it obviously to a solution here. So for example, in an acid base titration, perhaps you have a base up here, you could have an acid as well. and maybe we have an acid over here. And for example, we would add our base to our acid. And as you know, from using a burette, right, volume increases, right, as you go down on a burette there. So again, if you're in this area, you're at like 1.50 milliliters, usually two decimal places there when you take a reading. So we typically will add, say, a base to an acid or an acid to a base. And we typically want to continue on until we hit what is referred to as the equivalence point in the titration. The equivalence point in the titration is when the reaction is complete. In an acid-base titration, it is the moles of the acid will equal the moles of the base. So in an acid-base titration, when you reach the equivalence point, you'll basically have the exact same number of moles of acid and base at that exact point. And that is typically in a normal titration, if you were doing it, that is when you would want to stop your titration. Sometimes people refer to the endpoint of a titration. And the endpoint of a titration is basically where you stop your titration. And if you do a good titration, those two should be pretty close to each other. If you did it right, your endpoint where you lay up your titration should hopefully be close to the equivalence point. But how do we know if we're just doing a titration, when we should stop? And that is where we use an indicator, right? And an indicator is really kind of like a weak acid. It will kind of change color near the equivalence point. And there it is right there. That is everybody's favorite, which is like phenolphthalein, I think, spelled almost right, maybe. All right. That's phenolphthalein, yes. And you use that perhaps in Chem 50 when you did your titrations. Phenolphthalein is an acid-base indicator. It is what color in acidic solution? It is colorless, yes. In neutral solution, it is colorless as well. In basic solution, it is pink, right? So all indicators, as we'll talk about, pretty much work over a pH range. So for example, something like phenolphthalein is working somewhere in the pH range of 8.3 to like 10-ish. And right around 8.3, it is actually still colorless and gradually gets, I know my pen's red here, but as you go that way, are super dark pink if you're a titrating person like me, like super dark pink, I'm good, right? But if you've taken a chemistry class, which I imagine since you're sitting here, you've done that, they probably yelled at you want to stop when there is the first lightest color pink that you could see, like you have to hold like a piece of paper underneath it to see the light pink. And that's because that will put your equivalence point hopefully back at this range, which is probably where it should be. And we'll talk about the most common thing, and hopefully your titrations look something like that or lighter. Did anybody's? Yeah. I find that what used to help in Chem 50 is you say the magic two words of extra and credit, and then like everybody gets light pink. Before that, everybody's got the darkest pink known to man, and they're like, it's just light enough now for extra credit. But we will talk about really something that's probably happened maybe to you, are probably one of the most common phrases that you hear why people are titrating. And that most common phrase that you usually hear is this one here. I think it is, I just added 1 drop. It went super pink. Yeah. What happened? Like I had no color before, I added 1 drop, and now it's like super dark pink, right? And we're going to talk about why that happens and why, if you perhaps had a teacher and you showed them that, they might say that's a bad titration, you should do it again. If you did, maybe that wasn't the nicest thing for your teacher to tell you to do because you probably didn't need to. But we'll explain why they probably would make you do it again if you had a really dark pink. So we will talk about indicators, but essentially, obviously, the choice of an indicator is really important, and it is based on the type of titration that you do and where you would expect your equivalence point to be. So we're going to talk about 3 different types of titrations and sort of what's going on all the way through the titration, and you will be titration professionals, hopefully. We'll see. So the first type of titration we're going to talk about is a titration of a strong acid with a strong base. So we're going to look at like HCl, which is a strong acid with a little sodium hydroxide, which is a strong base. It's going to do an acid-base reaction here where we will get water and our friend's sodium chloride in this case. For reference sake here, up in the burette in this titration is the sodium hydroxide. So we're going to add the sodium hydroxide to our HCl in this case. So we're going to do that adding type situation. What we're looking at here on the screen is what is referred to as a titration curve. And a titration curve goes past the equivalence point, and you get this whole kind of traditional sort of S shape that occurs. And when we look at a titration curve for any type of titration that you do, there's really kind of four different parts to the titration curve that we look at. The very first part, right about here, is actually before you begin the titration. And that's sort of like the very first part of the titration curve. Then you decide I should probably titrate since I set it up and all that good stuff. So from the very first drop all the way to the equivalence point is sort of the second region in the titration. You've started your titration. In this case, you started adding some sodium hydroxide to your HCl. Then you come to that light pink perhaps area there of the equivalence point, and that is really the third part of the titration. One of the nice things about titrations that we will do is there's no worry. We're going to go right past the equivalence point, so you don't have to worry about getting the super light pink or anything like that when we do the lab. So if we continue on past the equivalence point, that's sort of the fourth part of the titration curve, and that is what happens basically as you go past the equivalence point. So we're going to talk about each of these four types, each of these four parts of this particular titration. And again, a reminder, what we're talking about here at this point is specific to this type of titration where you're dealing with a strong acid and a strong base, and it will be different when we're dealing with some other types of acids and bases in a second. So let's start with actually the very first part of this, and that is at the very beginning of the titration. Basically, no sodium hydroxide has been added. So at the very beginning, we have no sodium hydroxide added. That means if I got my burette here of sodium hydroxide, I did not turn it on yet. That means really the only thing I have in my flask, right, is my hydrochloric acid. So if I wanted to get the pH of my hydrochloric acid at this point, how do I get the pH of hydrochloric acid? Hydrochloric acid is what type of acid? It's strong, which means it's going to break apart into H plus, right? And Cl minus, which pretty much means I already know the H plus concentration. That means I could go directly into the pH equation at this point, and that will allow me to get the pH of my solution to start with, right? I don't have to worry about anything. I haven't added anything. I could just use the molarity. And in this case, since HCl is a monoprotic acid, pretty much the concentration of the HCl will be the concentration of the H plus. So we could go directly into our pH equation and get the pH here before we start titration. It should obviously be, as we can see here, should be acidic, right? Since we're starting with an acid only. All right, then let's talk about what happens in the second part here. So this is the part where I'm going to actually start adding some sodium hydroxide. So this is where I'm going to start dropping in some sodium hydroxide. So I'm going to start to add sodium hydroxide in this case. So I'm going to clearly get a reaction that's going to occur between the sodium hydroxide and the HCl. So I do need to have sort of an equation that's going to happen, and it's going to be that one I wrote on the previous page. We're going to have our HCl plus our sodium hydroxide. And that again is going to give us our water and our sodium chloride. So once you start the titration, you will need to do an ice table. Now, because I am adding sodium hydroxide to my hydrochloric acid, should I do this ice table in molarity or moles? Should do it in moles because I am adding volume. So kind of like what we talked about with the buffer, every time you add volume, molarity will change, but we should do it in moles. It will stay the same. And as we talked about, I think the other day as well, pretty much as you're doing titration, you're pretty much doing nothing but that of just kind of continuously adding volume along the way. So we're going to do an ice table here in moles, and I'm going to make up these numbers. So I'll say that one more time for future reference. These numbers are just being made up. We're going to start with here in our beaker, I'm just going with the wonderful number of 4 moles to start with. Now, I am clearly at this point before the equivalence point, right? And this is what I'm adding. If I am before the equivalence point, should the moles of my sodium hydroxide, which is what I'm adding, should it be less than, equal to, or greater than the moles that I'm starting with? It should be less than. And this is where we talked about at the equivalence point, we know that the moles are going to be the same, right? So if we're not at the equivalence point, we're getting up to equal moles, so we have less moles, right? So we know if whatever moles we're adding is less than what we start with, we're before the equivalence point. If we have equal moles, right, we should be at the equivalence point. And then if we have more moles of what we're adding, right, we should be past the equivalence point. So these are things you want to think about in your ice table. Could be really helpful. As we'll talk about these different types of titrations, sometimes it's really good to kind of know where you are in the titration, because it could kind of tell you what type of calculation you should be doing before you do the calculation. So it just makes it a lot easier. So at this point, since we are before the equivalence point, we should have less moles of what we're adding. Again, making up this number, I'm going to go with the magical number of 2, which seems a very nice, easy number. I'm going to go 0 here. Now, because we're before the equivalence point, all of the sodium hydroxide should get used up because, frankly, at this point, it is like the limiting reagent, right? We have less moles, and this guy is like the excess reagent. So once again here, we actually know what the change is going to be. It's going to be the moles of our sodium hydroxide that we're adding. And that means that when we get to equilibrium here, we will have 2 moles of this guy, 0, and 2 moles of that guy. Any questions on the ice table here? At this point, as I mentioned before, it is probably really good practice to convert these guys back into molarity. So we would need the total volume at this point. The total volume at this point would be how much acid we started with in the beaker, right? And how much sodium hydroxide we added, right? So that would give us our total volume at this point. So we would want to convert that to liters and divide by the total volume in liters. That will convert this back to molarity. We'll divide by the total volume. And once again here, our total volume would be the volume of acid plus the volume of base added. So at this point, if you're not sure what's going on, you could always use your ice table to sort of help you figure out what you have left at this point. We have sodium chloride and hydrochloric acid. By the way, should I use the Henderson-Hasselbalch equation here? Is that a buffer? That is not a buffer because HCl is a strong acid, right? So you cannot make a buffer out of a strong acid. So this is the place where I was talking about the Henderson-Hasselbalch equation that people screw up a lot, is when they go through titration problems, they end up with 2 numbers and they're like, cool, going into the Henderson-Hasselbalch equation. So this is not a buffer situation. You should not use the Henderson-Hasselbalch equation in this case. We do have 2 things here. We have this guy, which is a salt. And now you're going to tell me from the first part of chapter 14 that this salt is what type of salt? Is it acidic, basic, or neutral? It is a neutral salt. Very good, yeah. Which means we do not even need to worry about this guy, right? Because it's not going to affect the pH. So really what we're left with at this point is HCl, which is a strong acid still. So now we essentially have the molarity of our strong acid after it's reacted which is essentially our H plus concentration. And now we could go back into our pH equation at this point. So in this type of titration, in a strong acid, strong base titration, once you add the very first drop all the way up to the equivalence point, you do need to do one ice table. And really the purpose of the ice table is to figure out the new concentration of your strong acid. And once you have the new concentration of your strong acid, you pretty much could go into the pH equation, and that will get you to pH. Questions on that there? All right, so again, that's how you would handle any of the points along the way until you get to the equivalence point. So let's talk about the next spot, which is the equivalence point. Let's talk about what we actually see here on the graph. So we are raising our pH, right, as we're kind of adding our sodium hydroxide, which is expectedly what we would expect. And then what we kind of see here is we're kind of going vertical, right? We got a pretty big jump in pH to the equivalence point. And by the way, you also will have a jump in pH past the equivalence point, right? So in this range here, we're pretty much going straight vertical, yeah? So when I go straight kind of vertical in this case, right? The pH, is it changing a lot or a little? It is changing a lot, right? pH is on the Y there, right? So as we go straight vertical, the pH is changing a great deal here. So we have a big change in pH. How about the volume? Is the volume changing a lot? The volume's not, because if you draw like a straight line straight down, it's pretty much the same volume, right? And this is really what you see happen as you approach the equivalence point. And this is really the answer to the thing that people say is, I just added one drop. So although you only added one drop, right? Your one drop could be enough to change the pH by a lot. And why do you see that big color change in your indicator? Because something like phenolphthalein, which is 8.3 and colorless in this region, to 10, which is pink, when you added that one drop, it might have jumped your pH to up here, which is definitely in the 10-ish range, right? And that's going to be really pink, right? Now, let's say you were really careful and you added half a drop by adding some water and stuff as you're adding it, and you ended here at the equivalence point. Is there a big difference in the volume between, like, if I added just one extra drop and I ended up there versus I ended up here? Is there a real big difference in the actual volume that you added? No. Which is why, like, even if you have that really dark pink, it's not really that important. It's more important how much volume you actually added in each of your titrations. The reason your teacher might have yelled at you and said, that's a terrible titration, bad student. Hopefully they didn't say that, I hope. And you should do it again. They might have said that. Like, you should probably do that again. Is you could also be a titrating person like me who would just go in the lab, open the thing up, and just let it drain forever and shut it and go, pink, I'm done. I was done in like 10 minutes, right? And I was home. I heard the part of the instructions that said, get it pink, and I got it pink, you know? So, but if you did that and you weren't really careful as you're doing your titration, let's just say you're over here, that color pink here, and this color pink here is pretty much going to be the same, right? Which means now did I miss the equivalence point by a lot of volume? I did, right? Because I'm way, way past it. So that's why sometimes teachers will tell you, oh, it's too dark pink, you should do it again. But really, if you were really careful and you really only missed it by a drop or two in the type of calculations that you were doing, it probably wouldn't have made it that big of a difference in the overall calculation, because frankly, you would have had pretty much the same equivalence point volume. But again, that's why they usually will tell you that. So that's why we can see a really big change in the sort of indicator color, because it works off that pH range. And always, as you approach the equivalence point, you kind of just go straight up vertical. And that means that you're going to get a pretty big change in pH with not a lot of volume added. And as maybe some of you experienced, just like a drop or so is enough to cause that change to occur. So that's why you do see that big change with just that one drop. And that's why sometimes you could kind of dilute it down by adding some water as you're adding the drop, and it'll kind of dilute it and you won't have as big of a jump in sort of that pH. Any questions on that there? Okay, so now that we answer that age-old mystery question of why that happens, let's go to part 3 there on our very graffitied up graph there and see what's happening here. All right, so at part 3, we're at the equivalence point in this titration. So once again, clearly we're adding. So we'll have our reaction that's taking place, which is our HCl and our sodium hydroxide. And again, we'll get some water here and a little sodium chloride in this case. And once again, we are starting with this guy. We are adding this guy. And again, I'm going to use our ice table here, which is going to be in moles. So I'm going to use my same starting moles of 4 moles of my HCl. And if I'm at the equivalence point, what I should know is how many moles of sodium hydroxide should I have? I should have equal amounts. So I should have 4 moles here, right? Now, sometimes you're asked to figure out the pH at the equivalence point, and sometimes you need to figure out maybe the volume to reach the equivalence point. And sometimes they don't give you the volume to reach the equivalence point. How could I figure out the volume to reach the equivalence point in this case? So in this case, for example, I will know my molarity of my HCl. I'll know the volume of HCl I used. And for my sodium hydroxide, perhaps I only know the molarity. How would I figure out the volume to reach the equivalence point in this case? You can use M1 V1 equals M2 V2 in this case. By the way, you can only use that because it's actually a 1-to-1 relationship. If it's not a 1-to-1 relationship, you shouldn't use that because you'll have the wrong stoichiometry, right? And just so you know, M1 V1 equals M2 V2 is really just based off stoichiometry, just a shortcut to that. But it does work perfectly fine in this situation as long as it's a 1-to-1 relationship between the acid and the base. You also will know a couple of things. You will know the molarity of your sodium hydroxide, right? And you know by definition, the equivalence point, you should have the same number of moles, which means you have the molarity and the moles. You could just use the molarity formula, right? And you have the molarity, you have the moles, you can solve for liters, right? So that's another way that you could figure it out as well. You could do, again, the stoichiometry calculation where you take the volume of your acid times the molarity to get the moles of the acid, mole-to-mole relationship between the acid and the base, and then the moles of basically what I just did there, the moles of the base and the molarity to get to the liter. So there's a few different ways, and I say that because in a lot of titration problems, they will just simply ask you the question of, what is the pH at the equivalence point? They won't tell you how much you need to get there. And for certain parts of the calculation, you will need to figure out the volume needed to get to that equivalence point. Any questions on that there? All right, at this point, we'll have 0. The good news on this one is I don't think, hopefully, you can pick the wrong number since they're both the same. So I'm going to go with 4 in this case. And that's going to give me +4. That's going to give me nothing of my acid I started with, nothing of the base that I added, which is pretty much the definition of the equivalence point. And I will have 4 moles of this guy, which again, using the total volume, I can convert back to molarity. Once again, if we look at our ice table, the only thing we have left here is our salt. And as you correctly told me before, that is a neutral salt, which means the pH here should be 7. Yeah. No calculation actually needed because pretty much the only thing you made is water and a neutral salt, basically, right? Which is why these are sometimes referred to as acid-base neutralization reactions, right? Because you're basically making water in this case. And that salt that's floating around will have no effect on the pH because it's a neutral salt. So the nice thing about a titration of a strong acid, strong base is when you reach the equivalence point, frankly, the pH should always be neutral because you should only have a neutral salt basically left over with water, and you should hopefully have a neutral solution. Any questions on that there? All right, so at this point, we're here at number 3, and perhaps your indicator changed color, but perhaps you went to the school of titration like me, and that didn't stop you, and you said, I'm going to keep going because maybe that's pink, but not pink enough. I'm going to keep adding more in there. So let's talk about what happens if you go after the equivalence point here. So if we go to kind of the fourth part of this titration curve, which is after the equivalence point, we are still going to get our reaction that's going to occur between HCl and sodium hydroxide. Still going to give us water and sodium chloride. Again, we're starting with this guy. We are adding this guy. Again, here I'm going to use my initial moles of 4. Now that I am past the equivalence point, should the moles of sodium hydroxide be less than, equal to, or greater than the moles of the acid I'm starting with? Should be more, right? Because equal at the equivalence point, didn't stop you. You're just adding more base at this point. So you should have a lot more moles. So we'll go with a good number of 6, sounds like more. So we'll just make up 6 there. Now, something happens at this point because of that. What is going to be my change in this case? Is it the sodium hydroxide or is it the acid? It is the acid in this case because we actually now have more moles of the base than our acid. This guy now becomes our limiting reagent. This guy becomes like our excess reagent. Always, as I might have mentioned before, pick the smaller number, even though maybe your head will tell you you don't want to pick the smaller number. Pick the smaller number. You should never get a negative number, right? So that's a good way to remember that. So there will be times, and you might not think it will happen to you, but it will happen to you. You'll want to pick the other number, but pick the smaller number. So in this case, it's going to be -4, -4, and +4. And in this case here, zilch of that one, a couple of moles of that one, and 4 moles of this one. Just like normal, we're going to use our total volume at this point to convert them back into molarity. Once again, here we are left with 2 things. Is that a buffer? It is not a buffer. It's 2 different things, right? We still have our neutral salt, right? Which is neutral. So not even concerned about that guy. But now really what we have left over is sodium hydroxide, which is a strong base. And because that is a strong base at this point, and again, this is the importance of making sure that you write these equations, you do these ice tables, it just visually lets you see sort of what's there, and it just makes it a lot easier to sort of figure it out. Because that's a strong base, it's going to completely dissociate, and really this concentration is going to give us our hydroxide concentration, right? And the importance of this as well is that will not give us our pH, right? But it will give us our pOH first. Then we can subtract 14 to get to the pH at that point. So you do need to do past the equivalence point in this type of titration. You do need to do one ice table. And really the purpose of that ice table is to figure out how much of your strong base you got pretty much left over in that solution. And once you have that, that will get you your pOH and then to your pH. Any questions on any of those 4 parts of this titration curve here? All right. I think we will lay it up there and we'll do an example next time.